So here's some hints on these three final exam review problems that I hope will be helpful as you work on them. I am going to try to release solutions to this. I'm also going to try to release solutions to exam 3 now that I have everybody's, once I figured out I've had everybody's. But let me just say a few words about each one of these, and then we will call it a day. So the first problem, G is a finite group. We don't know what its order is, but some finite group over here. And we know that there's a homomorphism from G to Z mod 10. So Z mod 10, the additive group of integers mod 10. 0, 1, 2, ... up to 9. So we know that a homomorphism exists from G to Z mod 10. And what we're supposed to do is to prove that G must have a normal subgroup of index 2 and a normal subgroup of index 5. Let me give those names. So let's call the normal subgroup of index 2, let's call it H. Normal subgroup, and the index GH is 2. And then there's supposed to also be another normal subgroup of index 5, so let's call that one K. Normal subgroup of G, index 5. So let me ask the group that worked on this, where are you getting these subgroups from? What are your ideas? So you've made the right set of observations, right? In Z10, we know that there exists a subgroup of order 2. What is the subgroup of order 2 in Z mod 10? 5 and the identity. Yeah. And there also exists a subgroup of order 5. The multiples of 2, right? 0, 2, 4, 6, 8. So we know that those subgroups exist in Z mod 10. Now, can we realize these subgroups as the image of phi? So let's suppose that phi were a homomorphism, and let's suppose that the image of phi were this 0, 2, 4, 6, 8. What would that tell me? So 0 is hit, 2 is hit, 4, 6, and 8 are hit.
That means all of the elements of G go to one of those 5 elements.
Right. It means all the elements of G are going to land in one of these even residues mod 10, 0, 2, 4, 6, or 8. What would that tell me, if anything, about the normal subgroups of G? Or better yet, anytime you talk about normal subgroups, you can also talk about factor groups. What can that tell me, if anything, about the factor groups of G? What's the key result here?
Order 5.
One of the factor groups is order 5?
Well, one of the factor groups is order.
Yes. There's the theorem we want, right? The first isomorphism theorem. It says that any homomorphism out of G, first of all, its kernel will be a normal subgroup of G. Second of all, its image will be isomorphic to G modulo that kernel, right? The factor group of G by that kernel. And so if the image is all the evens over here, then that must mean that the kernel is a normal subgroup of G, and that G mod the kernel of this is isomorphic to this image, 0, 2, 4, 6, 8. So we'll be order 5. But keeping in mind that the factor group is exactly the group of cosets, how many cosets will the kernel of phi have inside of G if the factor group is isomorphic to this? We'll have 5 cosets. And if the kernel of G has 5 cosets in G, what does that mean the index of the kernel of phi is? It means the index of the kernel of phi is 5. Right? So that's the key sort of set of observations that you're making here, right? That if one of these homomorphisms exists, then its kernel is a normal subgroup that has exactly the desired index because of the first isomorphism theorem. So in problem 6, you're given the dihedral group of the hexagon and the subgroup I and TR cubed. And I'm asking which of the properties that would be necessary for the definition of a group are satisfied by the cosets of H in D6. So what are the properties that are necessary for a set of objects to be a group? Closure, inverse property, identity property. So,
And we're assuming that associativity is already.
yeah, let's add associativity as a fourth in parentheses. Okay. So we could show that any one of these is not satisfied and conclude that this subgroup is not, that the cosets don't form a group. Because what's the quick, under what circumstances do the cosets of a subgroup form a group?
If the plus
Say again? If I were to take these two elements, I and tr cubed, that forms my subgroup, H, right? And so then one of the cosets of this would be th, and it would have elements t and r cubed, right? And then I would also have rh, and that would have elements r, and then r times tr cubed, which is r tr to the 8th tr squared, I think is what I would get there.
closure, because it's
That certainly seems like it could be an issue. So why would closure be an issue?
the elements aren't abelian themselves, so it's not.
So the set of cosets of a subgroup form a group themselves when that subgroup is normal in the big group. Right? And that's not the case here, which is why I asked the question in this kind of weird way, because if I just asked you, are the cosets a group, you could say, no, they're not a group because this isn't a normal subgroup. But I wanted you to get real into the weeds here. So how does closure get violated? Let's say I take th and rh and I multiply them together as sets, right? So this is going to have 4 different elements in it, right? Each of the elements of th multiplied by each of the elements of rh. So in principle, we could have 4 elements. And when I actually carry that out, I get r squared from the product of t by tr squared. I get tr from the product of t by r. I get r cubed times r, which is r to the 4th. And then I get r cubed times tr squared, which is tr to the 5th. So why does that
That's not one of the cosets.
is not a coset, right? It's not a coset of H. So one of the good reasons why the cosets don't form a group is that the closure property is not satisfied. But because I wanted you to get practice here with cosets and also get practice using the definition of a group, investigate these other properties also. See whether or not the cosets have inverses that we can speak of, whether or not there is an identity in that system, and whether or not it's associative. All right, and for this last problem, you have a group G, any old group G. You have an element in the group, call it A, and then inside of G there's a center called ZG. And of course the center has the identity element in it, but then we also in this problem have another element Z inside of the center. Right? And we suppose that A and Z have finite order, so I'm going to follow the lead of the group that was working on this and introduce some notation. Call the order of A M and the order of Z N. And so then what we want to show is that the order of the product AZ is the least common multiple of M and N. Right? So we already have LCM theorems in 2 other contexts in the course. Where else have we seen an LCM for the order of an element? Permutations. So what kinds of permutations compose in this way? Disjoint cycles, right? In fact, disjoint permutations, no, right? Disjoint permutations. So disjoint permutations are one place we've seen this. What's another place? External direct product, right? That if I have an external direct product of 2 groups, then the ordered pair is the LCM of the orders of the individual things in that ordered pair. And so there's probably an analogy to make here, right? And the secret sauce to actually making it is that in general, if I want to know what the order of the product AZ is, so let's say I raise AZ to some power, and just as a clue, what if I raise it to the MN power, right? Well, ordinarily, this would be AZ, 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 dot, 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 done a total of MN times, right?
But they commute.
But what commutes?
A and Z commute together.
The A and Z commute. In particular, since Z belongs to the center, Z commutes with everything in the group G. So that gives it this, budging and line pass that lets it blow past anything it wants to. And so I can move all the Z's either all the way to the front of the line if I want to, or I could move them all the way to the back of the line if I want to, because they commute with everything. And so I can simplify this out to be A raised to the power Mn times z raised to the power mn. But what am I going to know about each of these?
The identity.
Yeah, this is going to be, respectively, the identity to the power n, the identity to the power m. So that's going to be the identity. So we know for sure that the order of the product AZ is going to be less than or equal to m times n. And so then the issue is how to get this order lower so that we're showing it's actually the least common multiple, not just necessarily the product. And for that,
Any other common multiple is gonna, if it's not the least, wouldn't satisfy the property of being in order, right?
because it needs to be the least.
positive.
Yeah, that's right. That's right.
However, there's no guarantee on face value that no multiple of those would not return that identity, right?
Well, no, I think the thing we just did is actually that guarantee.
It
Because
guarantees
this
that it
particular multiple,
must-
mn, must take you to the identity. But then, if you can show that this is true for any common multiple, then by definition of order, the least common multiple will be the order. So,
What if it's not a common multiple? We haven't proved that not being a common multiple doesn't give you the identity. That's kind of what I'm saying.
oh, I see what you're saying.
So that's my piece of why it wouldn't